In most cases, when you get a lipid panel, the LDL cholesterol will be calculated. If you get an actual measurement of LDL and find that the calculation overestimated it, should you be relieved? Well, be careful on that one. That's this week's topic. Stay tuned. So before we get into it, let's look at why LDL isn't just measured in the first place. Well, first of all, it's a cost and convenience factor. There is added cost to measuring LDL, and since these things are driven by insurance companies, if they can find a way to cut costs and pay less, they're going to do it. It takes specialized equipment to do it. It's not just your standard centrifuge that they use for the other ones. My CuraFit L7 unit that I use for home testing, it couldn't possibly measure LDL. So it's the same problem. Not all the labs are equipped to do it. And then finally, the reliability of the calculation for most patients. The calculations are pretty good for the most part for your average patient with an average lipid profile, something in the middle. And again, the insurance companies are driving cost reductions. They don't want to deal with the extra expense when a calculation meets their needs. Not necessarily the patients, but it meets their needs because they're looking at an entire population and the costs associated with that. There are many equations that are used. I found one paper that listed probably 24 of them, and they all revolve around the same theme. So I'm going to look at the 4 most common ones that I've come across. The first one is called the Friedewald equation. It's the oldest, it's the granddaddy of them all, and it's simply the LDL is estimated as the total cholesterol minus the HDL cholesterol minus the triglycerides divided by 5 if you're working in milligrams per deciliter, or triglycerides divided by 2.2 if you're working in millimoles per liter. Well, what's that all about? That is an estimate of the remnant cholesterol. So what they're doing is they're estimating the remnant cholesterol so that then they can estimate the LDL, the low density lipoproteins. So what they're doing is saying, well, we've measured total, we've measured HDL, everything else, we're just trying to figure out what proportion of that is LDL and what proportion of that is remnant cholesterol. A viewer pointed out to me that there is a modification to that equation where we can consider Lp(a) and multiply it by these factors in order to come up with LDL. In that case, a minor adjustment to it. For somebody with low Lp(a), this isn't going to make much of a difference. If you have a lot of Lp(a), this could make a considerable difference. And the reason the number is so small when you're dealing with millimoles per liter is that Lp(a) is typically measured in nanomoles per liter when it's using that unit. And quite often I will get my results in those units. So that's why the difference there. So it's just a way for accounting for some discrepancies that are quite often seen in the differences between this equation and the measured amount. Then there's the Martin-Hopkins adjustment, which is really the Friedewald equation, except instead of dividing by 5 or 2.2, there's a table where they look up a coefficient to apply. And the lookup depends on the triglycerides level and the non-HDL, which is just the total minus the HDL. And between those two things, they look up this coefficient and they use that. Then there's the Sampson equation, and that looks a little different. This is the way it's presented in the papers. Non-HDL minus 0.16 times the triglycerides, or if we're in millimoles per liter, 0.36 times the triglycerides. I'm a software engineer by trade. Well, I'm retired now, but I always look at things like this and I try simplifying them, getting them down to say, these are all very common. They're really the same equation with different coefficients or fudge factors, if that's what you want to call them. And this is what they really come down to. They all say the LDL is the total minus the HDL minus an estimate of the remnant cholesterol with this little caveat on that modified Friedewald one where they consider Lp(a). Now you may look at the Sampson one at the bottom, it's still showing on the screen, and say, well, that doesn't look the same. What is non-HDL? It's total minus HDL. That is actually the same. And then 0.16 times the trigs, take the reciprocal of that, that's the same as trigs divided by 6.25. So all these equations are really the same thing. They're just messing around with coefficients, or again, fudge factors, if that's what you want to call them. All 4 of them will break down to this. Only one of them actually uses coefficient 2. For the others, it's 0. But this is what they all look like. In the end, it's an estimate that's trying to take the part that they haven't measured and figure out how much is remnant cholesterol, which is VLDL, very low density lipoproteins, IDL, intermediate density lipoproteins, that sort of thing, and how much is LDL. So if you were wondering, this is the Martin-Hopkins coefficients tables. They look at the non-HDL cholesterol for the columns, and for the rows, they look at the triglycerides level. What I found interesting with this is I put this into an Excel spreadsheet, and I highlighted all the cells with coefficients in them. The average was 5.2. So the Friedewald equation, it's the same as this more sophisticated use of coefficients. It's just taking the average of all of them. And if you take the bottom half of these charts, in other words, the higher levels of triglycerides, the coefficients average out to 6.25, which is exactly the Sampson equation. And the Sampson equation is used basically for people with higher triglyceride levels. We can see where those come from. The Martin-Hopkins coefficients table is just more discrete, and for that reason, it's more accurate. My last test results from the Quest lab did state that they used the Martin-Hopkins equation in calculating my LDL. So what are the implications of this? Let's look at a couple of examples. Example one, suppose your calculated LDL came out to be very high by some people's standards, 180 milligrams per deciliter. And then it got measured and it came out to be 160, or you can see the values here, 4.7 millimoles per liter or 4.1 millimoles per liter. Should you be excited? What does this really mean? The conclusion there is that your remnant cholesterol is higher than what was calculated by about 20 milligrams per deciliter or 0.6 millimoles per liter. So whether you buy into the HDL is good, LDL is bad paradigm, for certain, remnant cholesterol is ugly. What you've done is traded some bad for some ugly. Getting that lower value when measured is not good news for you. It means that your lipid panel is a little bit worse than what the calculation said it was. Another example, suppose your total cholesterol is 200, you're arguing with your doctor and you finally convince him, well, that's borderline in his mind. To me, it's not a problem at all. 220, some studies have shown, is actually the healthiest level at a population level, not necessarily for individuals. And your HDL is 50. So you convince your doctor, I don't need a statin. I don't want to take a statin for this. And he says, okay, but I really want your LDL down. I want your LDL to be 70. So you have these values and you ask, well, which LDL value is healthier given we're going to keep the total at 200 and we're going to keep the HDL at 50. Those are both very good values. Would you be better off finding out that your LDL is 140 or 70 as the doctor is targeting it? Now, in fairness, this is a contrived example. If your doctor is trying to get you down to 70, he's probably also trying to get you under 200, which is not justified, but that's the way it is. But if he was happy with 200 and just said, okay, get your LDL down to 70 and I'm happy with the 200 and the 50, he really shouldn't be, because the remnant cholesterol in that first example, when you have 140 for LDL, the remnant is only 10. That's a very low remnant cholesterol level. In the second case, it's 80. That's through the roof for remnant cholesterol. As an independent indicator of cardiovascular risk, 80 is bad and 10 is very good. And if we take the Martin-Hopkins equation and we reverse engineer that, this implies a triglyceride level of 33 in the first case or 640. It's through the roof in that second case. You really did have this contrived lipid panel that I've come up with of 200 milligrams total, HDL of 50 and 70 for LDL. That's a very unhealthy profile. Before I go on to my closing thoughts, I just wanted to insert this. This is something I did the day after I recorded the video. I wanted to answer the question, what happens if you don't fast before having a lipid panel take? It's kind of related to this whole issue about LDL calculations. So I did this quick little experiment. I took a lipid panel using my CuraFit L7 unit after a normal 12-hour fast overnight, and then I ate a carbohydrate-rich all-processed breakfast, the crap breakfast. Much different than what I would eat if I wasn't sacrificing my body for science in this way. I had 68 grams of carbs, which is way more than I would eat normally in an entire day, but I wanted to create an extreme situation. I then went through about an hour of normal activities in the morning, getting dressed, letting the dog out, washing dishes, that sort of thing, just to simulate what it might be like for a typical person who got up in the morning, had breakfast, and then went into the office to have the lipid panel taken because their doctor said, oh, don't bother fasting anymore, because some doctors say that. What I expected would be that the trigs alone would go up in this situation, and therefore the calculated LDL would go down according to the equations that we've been using. That's not exactly what happened. So here are the results of this little experiment. The total cholesterol went up by a little bit less than 10%. HDL held pretty steady. Triglycerides went up quite a bit. The non-HDL went up. LDL calculation, according to the Friedewald equation, is under LDL-F here, and you see that it went up by nearly 10%. By the Martin-Hopkins equation, went up by a similar amount. And the triglycerides over HDL ratio went up from under 2. You know, I consider 2 being the gold standard, 1 being the platinum standard. I occasionally get a value under 1. Usually I'm between 1 and 2. And when not fasting, it was over 2, which is above the gold standard. There's a couple caveats here. First, I don't know how much of the variation here is just a result of built-in or kind of native variation of this test kit and how much was actually from the experiment. But it's an interesting difference because these values are about 10% different. That could, for somebody, make the difference between, say, an LDL level of 135 and 150. That could be enough to make the doctor want to change a recommendation. So you should always fast, even if the doctor says don't bother fasting. Get your blood test in the morning after your normal overnight fast. The other caveat, of course, this is an N of 1 experiment. It's just me, but these are the results. And I thought they were interesting enough to share. It's one data set. I could probably do this experiment many more times, except the test strips are rather expensive and I don't want to use too many of them. So let's get on to my closing thoughts. So this is just a quick tutorial on the likely way that your LDL is being reported to you. The one time I got a measured LDL, it was very consistent with both the modified Friedewald equation, the one that considers the Lp(a), and with the Martin-Hopkins values. I'm satisfied with the Martin-Hopkins equation being used. For my particular characteristic lipid panel, it's very close. For those viewers in the extremes of lower trigs, such as somebody who's an extreme lean mass hyperresponder, the Martin-Hopkins equation is certainly better than the Friedewald equation. If you're a lean mass hyperresponder, you're more in a situation where I think it's the quality of the LDL that's probably more important. For example, is it pattern A or is it pattern B? It's probably pattern A. Almost by definition it's pattern A because of the triglycerides level and the HDL level, but that's a more important consideration. Well, what is the percentage of LDL particles that are small, dense LDL particles? You can get a LDL particle test, and that is different than the standard LDL measured test, which is a mass density. But for me, my small, dense LDL particles only make up about 15 to 19% of the total LDL in my system. So I think that's more meaningful than the total measurement, more than saying, well, your LDL level is whatever it is. The bottom line is you need to be told, or you should be told, whether the LDL was measured or calculated, and if it was calculated, what equation was used. So that's what I got on this topic. I know it wasn't specific to statins, but it's related since your doctor is likely to use LDL as one data point where he's trying to convince you that your life depends on taking this little pill. And it's good to know exactly where it came from. So if you appreciate this content, please like, share, subscribe, and comment on this topic or others you'd like me to cover. And if you haven't seen this video, I recommend you take a look at it now. Thanks for listening.